guess what, guys? You've made it to the last video for Unit 7 and the last video for AP Physics. It's kind of crazy. This is video 3. It's going to be about angular momentum and angular impulse. Let's just get right into it. We know in translational kinematics, we have the impulse momentum theorem, which states that J, or impulse, is equal to the change in P, or the change in momentum. Now, why is there a random line there? This is frequently expanded out to be force times time, or change in time, really, is equal to the mass of an object times its change in velocity. This is basically saying that the force applied to the object, right, for a given amount of time will lead to a change in velocity, right? And this we know is derived from Newton's second law. We go from F equals ma. A is just equal to change in velocity over change in time. So then we replace that, m times change in velocity over change in time, and we just multiply both sides by change in time to get the impulse momentum theorem, right? Well, there is also a rotational analog for this as well. Instead of force, we have a torque. The time stays the same. It's still change in time. And instead of the mass, it's rotational inertia, which I talked about last video. And it's going to be the change in angular velocity instead of translational velocity. This also does come from the second law variant. We have I alpha, right? Alpha is equal to change in omega over change in time. So then we just multiply both sides, right? Not going to write that out. Do note, though, that this formula for angular momentum, or at least the change of momentum, it's represented with the variable L, by the way. Interestingly enough, there's no variable for the angular impulse or the left side of this equation. But yeah, this is going to be change in L. Like I was saying, though, this I times change in omega, it's only for extended objects. So like an object moving about an axis that goes in it. For example, like a wheel, it rotates about an axis, that axis being its center point, right? If I was spinning a disc in like a disc or like a CD player, right, then it's rotating about its center point, but that axis is like, it's going straight up, right? So it's rotating about that axis and it goes through it. What's some other examples? I guess like the tops that you spin on a table, right? It's rotating about that vertical axis that goes through its center of mass and everything, right? Now, for point objects, or objects moving in a circular path about a point, the formula for angular momentum is a little different. A point object, just an example, let's say that's the center of a path, right? If something's just moving like this, like for example, if I'm walking around a track, I don't know, this is a really bad example. Something just rolling in a circle, I don't know. Yeah, let's go with that. If it's rolling in a circle, then its angular momentum, it's simply going to be the radius of this path, right? So r, it's a really bad r times p. P is your linear momentum. So this can be expanded to r times mass times velocity. This is an important distinction to know, though, because there are times where you're going to want to use rotational inertia times angular velocity. There are times where you're going to want to use radius times linear momentum. Just know the distinction. Do know that sometimes you'll be able you'll be asked to compare some angular scenarios to some linear motion ones. Just as an example, like if I have two disks, let's say one spinning clockwise at a certain angular velocity of omega, and the other is spinning counterclockwise at omega, right? Then like what's gonna happen if I like put the two disks onto each other and they stick together? Well, then that's going to mean that they spin with a combined angular velocity of 0. It's basically the equivalent of, let's say I have two of these, right? And we'll say that they have the same mass. I forgot to say the disks are identical, but let's say they both have a mass m. If they're both rushing towards each other with the same velocity v, then they're eventually just going to collide at m and m, where v is just 0, right? Probably should add some v naughts there. Just as another example, like if I have a disk at rest and another disk above it is then, oh wait, no. A disk is like moving with an angular velocity of omega naught, and a disk above that is at rest. If that disk is then dropped onto the disk that's moving, right? What's going to happen? Then they're going to, you know, like stick together, and then like, well, they might not even necessarily stick together. It just depends on the scenario, but that is analogous to like this scenario, right? We might have M1. This one might be moving, right? We'll say V naught. This one can be M2, right? And we'll say that one's at rest. This is just the same as a scenario where it looks like, you know, M1, M2, they move together with the combined velocity of V, right? So the notion of a collision still exists in like an angular, in an angular context, but it's, how do I phrase this? You usually don't have to think about collisions in terms of like, oh, well, like, determine the speed. You know, that's not something that's too common. Now, just like impulse, angular impulse can be determined from a graph. In this case, it's going to be an area bound by the curve for net torque versus time graph. That is going to be the angular impulse, right? The angular impulse is, of course, also equal to the change of momentum. Angular momentum, I should say. This is really similar to, like, you know, I talked about this in video 1, but graphing ideas for, like, you know, your linear displacement, linear velocity, linear acceleration, time, those all apply to angular displacement, angular velocity, angular acceleration, and time, right? The ideas with graphing, they honestly really just stay the same. Last thing I want to say in this video, conservation of angular momentum is a thing that exists, just like how conservation of momentum, linear momentum, is a thing that exists, right? To practice some angular momentum conservation, let's do a little practice problem. Let's say I have this rod. This could be, give me some time here. This is a rod, okay? This black circle at the end, it's a pivot point, so it rotates about this black end, okay? Let's say that the mass of the rod is equal to 6 kilograms. Let's go with 6. The length of the rod, length of the rod is 3 meters. Don't get that L confused with the angular momentum L, by the way. And the rotational inertia is going to be 1/3 times the mass times L squared. And let's say we have a ball charging towards this ball. Let's give it a color. Let's go with this little maroon brown. Yeah, I like that. Let's say this has a mass of 3 kilograms, and let's say its initial velocity is 10 kilograms. No, kilograms. What am I saying? Meters per second. So this ball, it's gonna hit the rod at the end of the rod, as shown, right? After colliding, we'll say the ball just completely comes to a stop, and it converts all of its it converts all of its momentum to the rod. What is the angular velocity of the rod after this collision? All right, let's assume that you've given this a shot. This one, like I kind of hinted at, it hinges on conservation of angular momentum. So we'll start with our conservation equation. We have the initial angular momentum is equal to the final angular momentum. Now I'm going to expand both of these. This means that the initial momentum, angular momentum of the ball, all right, B, looks like lob, and then the initial velocity, the initial angular momentum of the rod must equal the final angular momentum of the ball plus the final angular momentum of the rod. Now in this case, the rod has no initial momentum, or like both linear and angular momentum, because it's at rest, right? And the ball also has no angular momentum after the collision because it's completely at rest afterwards, right? Now we can do some little substituting. In this case, the ball's angular momentum can be used with the formula for point object that I talked about here, right? This r times p. So we'll say that this side is r times p. The other side is equal to rotational inertia times omega, right? Now I'm going to expand p here. We have r times the mass of the ball times velocity, v naught, I guess I should say. This is equal to 1/3 times the mass of the rod times L squared multiplied by omega, right? Now, in this case, the radius, so the r term, that's actually just equal to L. So I'm going to just erase the r, place that with an L. Now I'm going to just simply rearrange this equation to solve for omega. Omega, in this case, is equal to uh, L times the mass of the ball times the initial velocity divided by 1/3 times the mass of the rod times L squared. In this case, this L on top and the square cancel out. I'm going to bring this up here. The 1/3 in the denominator is just a 3 in the numerator. So now I have omega is equal to 3 times the mass of the ball times the initial velocity over length times the mass of the rod. I don't know why I started writing out ball and rod in its full terms instead of just using like B and R, but oh well, we'll go with it. Omega 3 times, oh, I might not have space, 3 kilograms times 10 meters per second. That's fitting. What about the denominator? 3 meters times 6 kilograms. Okay, they fit. We're good. Let's see here. Let's do some simplifying. That cancels out. That becomes a 2. So then that's just 5. Those units cancel out. Those units cancel out. So then we're left with omega is equal to 5. And we know that angular velocity has units of radians per second. That's a final answer. That is the angular velocity of the rod after the collision. Well, I guess that's it for Unit 7. Just as always, practice problems are available. There will be a link to those in the description. There are 7 practice problems this time around. As always, there's answers and explanations. Interestingly enough, this set of practice problems, none of the questions have answer options. So have fun with that. I can't even really say see you next time anymore, huh? We're at the end of the video making. Who knows? Maybe I'll pull a Unit 5 and make some more videos. But let's just go with the safe option of see you next time and good luck on that AP exam.